Swayam Prabha. Digital India. Educated India.
In this lecture, we will continue our discussion on normal shock waves, and we will also introduce Mach waves and oblique shock waves. In our previous lecture, we were discussing about the hypothetical state changes of a compressible flow, and thereby we came across the concept of characteristic Mach number m star and also a star, when we either accelerate or decelerate a moving flow to a sonic condition. Additionally, we also talked about slowing down such a compressible flow isentropically to 0 velocity, and thereby we discussed about the stagnation conditions. Let us recall about the energy equation and try to look at it from a calorically perfect point of view. In that case, the energy equation will be written in this way. Remember that this is nothing but H at the station 1 and at the station 2 respectively, and note that the above form of energy equation is of course valid only for adiabatic flows, otherwise you have to include the heat transfer term. And then what we are going to do is we will remove the subscripts for station 1 and imagine that the gas reaches a stagnation condition at station 2. All right. So, we are talking about slowing down the fluid particle from a state of motion to 0 velocity, and therefore, we will bring in the concept of isentropic slowdown in due course, but not immediately at this point. So, when it slows down to 0 velocity, we have the concept of stagnation temperature coming up. So, the static part gets absorbed into the dynamic part gets absorbed into the static part, and therefore, the static part gets elevated to the stagnation condition. Now, we need to take note of a very important point here, that when we are defining stagnation temperature T naught, the flow needs to be adiabatically slowed down. It does not necessarily need to be slowed down isentropically. This is a very important point, because the energy equation is based on an adiabatic assumption, nothing more. We are not saying that it has to be necessarily reversibly adiabatic. Therefore, just adiabatic condition is sufficient in order to bring in the concept of T naught. Once you have done that, you can evolve an expression for T naught by T, which is nothing but the ratio of stagnation temperature to static temperature. And then what you need to do is you divide this equation by Cp T, and then you can show finally it comes out to be 1 plus gamma minus 1 by 2 m square. Therefore, the stagnation temperature to static temperature ratio is given by this expression. So, higher the Mach number of the flow, higher would be the stagnation temperature with respect to the static temperature. Now, if the state 2 was reached by the gas through an isentropic process instead of just an adiabatic one, that means you are bringing in the concept of reversible adiabatic, then what can we do? We could use the following relation to connect the stagnation pressure and stagnation density with stagnation temperature. So, that is the additional connection you will be able to bring in. So, this is the isentropic condition connecting pressure, density and temperature ratios. Thereby, now you can say that if it is an isentropic deceleration, then the pressure ratio P naught by P will now be a function of m using this equation, or rho naught by rho, which is the stagnation density ratio, will again be a function like this. You need to take note of the differences in the indices here. Okay. So, this is stagnation pressure, this is stagnation density, and now you have a connection between the stagnation pressure ratio and density ratio with Mach number. Let us look at some more relations related to normal shock. We recall that the continuity, momentum and energy equations for the case of a normal shock placed inside a one dimensional control volume, that we have already derived. We know that what are the fluxes which are balanced across a normal shock, and we had 5 equations to solve and 5 unknowns to be worked out from those equations algebraically. If you do that, you will be able to come up with the following equations, which show you the change in Mach number or density or velocity or pressure, temperature, enthalpy, etc. So, it is only those 5 equations which have to be solved ultimately, but additionally if you bring in the concept of A star, M star in between, the derivations become simpler, and that is why we have already introduced these terms. So, you can try deriving these equations on your own later on as a homework problem, or try to refer to some of the references which I have already stated in earlier lectures, in order to go through the detailed derivations of these equations, which we are stating directly without proof. So, you use this equation to find out the change in Mach number across the normal shock, and we are talking about the upstream state as 1, the downstream state as 2, and here is the normal shock standing in between the upstream and downstream locations 1 and 2. You will find that if you substitute a supersonic Mach number, that means any value m1 greater than 1 on the right hand side, and consider gamma is equal to 1.4, which works fine with air at standard conditions, then you will always find that m2 will turn out to be less than 1. It is not only less than m1, but it also turns out to be less than 1, which means a supersonic flow becomes subsonic on crossing a normal shock. Also remember that you do need a supersonic flow for a normal shock to exist. A normal shock can exist only under such conditions. It cannot exist in a subsonic condition, for example. In fact, below sonic condition, you will never see the existence of a shock. So, that is the learning from the Mach number equation. Of course, we end up ignoring the negative root from this equation. What about the density ratio or velocity ratio equation? You will find that the Mach number becoming less than 1 would indicate that u2 becomes less than u1. That means the velocity drops, and drops in what manner? It is an abrupt drop. Velocity was higher upstream of the shock. So, u1 was larger, u2 becomes abruptly smaller, and this is where the shock lies. There is almost a sudden jump in the velocity, a sudden reduction. What does density do? Density compensates. The density rises across the normal shock to compensate. Why? Because ultimately the product of density and velocity has to remain constant. That is what your steady continuity equation has conveyed. So, those will come out from an equation like this, where again you find that if you just substitute the upstream Mach number here on the right hand side of the equation, you will get those ratios. So, we have seen that m 2 has been expressed as a function of m 1. So, let us call the function as m. Similarly, rho 2 by rho 1 or u 2 by u 1 has been expressed by some other function, let us say d m 1, d for density. If you go to the next equation, which shows you the pressure ratio, you will find that if you substitute a value of m 1 greater than 1 over here, naturally this will give you a value which is positive, which when multiplied with this term, which is also positive, will give you a value greater than 1, which means the pressure beyond the normal shock is higher. That means, the normal shock has created a compression in the flow. If the m 1 is larger, there could be significant compression of the flow produced by the shock. In fact, this is one of the mechanisms by which compression is produced in high speed flows, sometimes even with a purpose. Let us come to temperature or enthalpy ratio, that is static enthalpy ratio. These are equivalent in the case of calorically perfect gas, where your Cp is a constant essentially. So, here again you just need to have Mach number and your job is done. You just substitute it on the right hand side and you get the ratio. So, in the previous equation you had P 2 by P 1, that is the pressure ratio expressed as a function P m 1, and here maybe you can express temperature ratio